As we begin our discussion of conjugated systems, we're going to start by looking at a molecular orbital description of these conjugated systems. It can be helpful to use molecular orbital theory. Often we're going to use valence bond theory. Okay, we talk about hybridization, we think about how these hybridized orbitals overlap with each other, and often that gives us enough information to be able to work with. But sometimes we need to go deeper and we need to use molecular orbital theory. Okay, we don't want to use it all the time because it's much harder, but sometimes we need that extra detail. Okay, so let's just take a look at molecular orbital theory when it comes to a very simple organic molecule, H2, hydrogen. So with MO theory, what we're focusing on is the linear combination of atomic orbitals to give molecular orbitals. Linear combination of atomic orbitals to give molecular orbitals. So this tells us two things. Okay, one, it tells us that however many atomic orbitals we have, that's going to give us the same number of molecular orbitals. And it tells us that the molecular orbitals arise from a linear combination. Okay, we just add them up. All right, so what does this look like? When we have our atomic orbitals, so this is an atomic orbital for hydrogen, and this is an atomic orbital for the other hydrogen. Both of these orbitals can be in the same phase, and that is represented by blue in this case. So if we have this orbital and this orbital in phase, they add up to give us a new molecular orbital. It's called a sigma orbital. Sigma because the electron density is along the axis that joins the atoms. This is a sigma bonding orbital because we have electron density all the way through. It's also possible for the atomic orbitals to combine out of phase. So blue is one phase and red is a different phase. And so if we try to add these together, they actually subtract from each other. And so what we get is a molecular orbital that looks like this. So we have electron density out here, we have electron density out here, but here we have a node where there is no electron density. This one is called a sigma star. Okay, it's sigma because technically we still have the electron density along this axis, not way above and way below, but star because we have a node. All right, so there's no advantage because there's no electron density in between the two nuclei holding them together. So from two atomic orbitals combining in different ways, we get two molecular orbitals, a sigma and a sigma star. The sigma is the lower energy because we have electron density between the two nuclei. That's going to make it stable. And then our sigma star is antibonding, that's higher energy, because there's no advantage. There's no electrons in between the nuclei holding those atoms to each other. We put together this information as a molecular orbital diagram. What we do is we write the atomic orbitals on the outside. So this is the hydrogen 1s orbital, and this is another hydrogen 1s orbital for our two different hydrogen atoms. And then in the middle, we write our molecular orbitals. Down here is our sigma bonding orbital, and up here is our sigma star antibonding orbital. Now, with our molecular orbital diagram, we fill in our electrons. Okay, we're following all the rules that you learned back in Gen Chem, the Aufbau principle, the Pauli exclusion principle, Hund's rule. We build up from the bottom. We have 1, 2 electrons, so we fill those in. We have 1, 2 electrons. So in the hydrogen molecule, we have 2 electrons in a bonding orbital. We have 0 electrons in an antibonding orbital. So this shows us that H2 is more stable as a molecule than it is as individual atoms. So the good news about molecular orbital theory is that it gives you a lot of information. The bad news is that it gets complicated pretty quickly. But more good news is that we can look at pi systems separately from sigma systems. All right, so let's take a look at a nice simple compound, ethylene. And when we think about ethylene, we're going to think about the p orbitals. So this carbon has a p orbital and this carbon has a p orbital. This is the atomic orbital that corresponds to the first carbon. This is the atomic orbital that corresponds to the second carbon, and they can be added together, right? The linear combination of these atomic orbitals. Now, there are two possibilities. If both of these orbitals are in phase, like this, then they're going to overlap, and that leads to a bonding pi orbital. Okay, this is a pi molecular orbital. If, on the other hand, the p orbitals are aligned out of phase, so that red is on blue and blue is on red, then this gives us an anti-bonding, so a pi star molecular orbital. All right, so we already have this node which exists in the p orbitals. So we already have this node, but in an anti-bonding, we get a node here as well. So we have some electron density, but not in between the atoms. Okay, so the pi molecular orbital is lower energy, the pi star is going to be higher energy because of this extra node. When we think about this in a molecular orbital diagram, the pi molecular orbital is going to be lower energy, and the pi star molecular orbital is going to be higher energy. Because we're talking about ethylene, we have 2 pi electrons, and so both of those would be in the pi molecular orbital. Now, what if we take that same approach and apply it to a conjugated diene? So this is 1,3-butadiene, and we have a p, 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 and p. So we have 4 p orbitals. Now, how can these atomic orbitals be added together? They can all be added up so that all the blues are on the bottom, all the reds are on the top. That gives us one option. It could be 2 of these aligned, and then the other 2 are the opposite way, so blue, blue, red, red. It could be blue, red, red, blue, or it could be alternating all the way through blue, red, blue, red. All of these have the node of a p orbital, so they're the same that way. So the first one has no additional nodes, so this is a pi bonding orbital, and we can call this one pi 1. The next one, we have 1 additional node, so it's a little bit higher energy than pi 1, but it is still a pretty good one. It is still a bonding orbital. This one is called pi 2. The next one, we have 2 additional nodes. So now we have an anti-bonding. This is called pi star 3. And then here we have 3 new nodes. So this one is another anti-bonding. So pi 4, pi star 4. Where are our electrons? Right, we started out with 4 p orbitals. We have 2 pi electrons here and 2 pi electrons here. So let's fill them in. We have 1, 2, 3, 4 electrons. So this shows us that all of our p electrons are in pi 1 and pi 2. So they're in bonding molecular orbitals. And thinking about these 2 molecular orbitals, in at least one of them, we have electron density in the pi system, including in between carbons 2 and 3. All right, so we have this extended pi system. So while we write this as an alternating double bond, double bond, molecular orbital theory shows us an explanation where we can see that there is pi electron density all the way through this extended pi system. So molecular orbital theory provides us an explanation that is consistent with experimental observations, right? So we can think of this as having partial double bond character here, which is what we see experimentally. There is limited rotation around here because we have partial double bond character. This undergoes different reactivity than what we see with isolated dienes or with individual alkenes because conjugation, because this extended pi system gives it different reactivity and different characteristics. Finally, let's consider molecular orbital theory regarding allylic systems. Now, if we have an allylic carbocation, it might look like this. If we have an allylic radical, it might look like this. And if we have an allylic anion, it might look like this. So each of these are incomplete structures, but we're focusing on the 3 carbons of the allylic unit. That means we have to focus on 1, 2, 3 p orbitals. As we consider how 3 p orbitals can linearly combine, okay, here we're using blue and green. So if this is blue, 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 and then we have green, green, green. Now, one possibility is that they add up together all in phase, and that leads to this molecular orbital down here. Another possibility is that these outer ones are in phase, but the top one is in the opposite phase, and that means we're going to get 2 nodes here, and that's what we have in the top molecular orbital. And then the third option, which doesn't look as obvious, if this one and this one are in opposite phase, and then this is just a node, that gives us the middle molecular orbital. So from 3 atomic orbitals, we get 3 molecular orbitals. All of them have the node because they are p orbitals. In the bottom one, our bonding pi orbital, this one has no additional nodes. In the middle one, this is our non-bonding pi orbital. We have 1 additional node. And then in the top one, our anti-bonding, we have 2 additional nodes. So higher in energy as we go from fewer nodes to more nodes. So let's think about the different species. When we're looking at an allylic carbocation, we have 2 pi electrons and no extra electrons here. So that means we have 2 electrons in the allylic system. They are in the bonding orbital, and therefore the allylic carbocation is stable. Okay, so this is the carbocation. Next, let's look at the radical. With the radical, we have 2 pi electrons plus 1 more electron that's in the pi system. So that means we have 2 electrons down here and 1 electron here. And because we have more electrons in the bonding orbital and only 1 in the non-bonding, overall it's more stable than if these were 3 isolated p orbitals. And finally, if we're looking at our carbanion, now we have 2 pi electrons, plus these would also be in the pi system, so we have 4 electrons to work with. And so we're going to have 2 of them here in the bonding orbital, 2 of them in the non-bonding orbital, but no electrons in the anti-bonding orbital. So in each case, whether we're talking about an allylic carbocation, radical, or anion, we have increased stability because of the delocalized pi system, because all 3 carbons are involved in a conjugated pi system.